a great welcome to the series on Abaqus. Myself, Jarajan P. This is tutorial number 14 and provides the damage analysis of a steel specimen in tension. So as usual, let us first see the problem statement. So the specimen that will be investigated in this tutorial is shown here. It is essentially a square rod of section 5 by 5 mm and it has got a length of 60 millimeters. For 1/3 of the length, the specimen is clamped and the displacement loading is applied through the next 1/3 end. So a lot of data need to be fed into Abaqus for the damage analysis of this bar. So first of all, let us focus on the elastoplastic data. So the steel grade that will be used for this specimen will be S355 grade. The mass density also it will not be used for the static analysis. It is given here 7.8 into 10⁻⁶ kg per millimeter cube. And the E value, that is the modulus of elasticity, it is 2 into 10⁵ MPa. Poisson's ratio is 0.3. And the plasticity will be provided as per the true stress strain data. As we know that the stress strain data can be either engineering or it can be true. But as far as the damage analysis is concerned, as we are interested in predicting the stress state at very large deformations, it will be very much relevant to feed only the true stress strain data. And the typical true stress strain data for the S355 grade steel is as shown here. Now coming to the damage data, we need to specify some critical parameters to Abaqus, like for example the fracture strain, that is the strain at which the fracture is considered to be initiated, that is provided here as a 0.24, and then the stress triaxiality. This is a very important term, and obviously what I think is that I need to provide a separate detailed tutorial on stress triaxiality, what it is and what is implication of the fracture strain, etc. And for this tutorial we had provided the stress triaxiality as 0.33 and the strain rate is given as 0.001, and Abaqus provides you the basically two methods for predicting the damage evaluation. And in this case, the damage evaluation is predicted or defined through the displacement monitoring. And the displacement at failure is provided to Abaqus as 2 millimeters. And as already stated, the specimen will be subjected to a displacement loading. And how the displacement loading of maximum 15 mm is applied is shown here. At time t equal to 0, you can see that the displacement is 0. And obviously, it increases linearly to a maximum of 15 mm at a time period of 1.0. So let us go to the Abaqus. So as usual, let us start with creating the part using the module part. So here we have got only a single part. I'll call it as a bar. And all these modeling defaults will be kept the same. And here I will keep the approximate size as a 10. Continue. Let us create a cross section. We shall draw a rectangle with one vertex will be -2.5 comma -2.5, okay, and then +2.5 comma +2.5. Okay, so we have created the cross section for the rod. Now let us just extrude it. So we know that the length of the rod is 60 mm, so provide the depth as 60, so that is okay. So we find that yes, the part is already created for us. Let us switch over to the module property. So let us first of all create a new property. Let me call it as a steel. So steel. Now let us start providing the mass density, though it will not be used. Okay, let us provide it. So this is my 7.8, 7.5. 7.8 e raised to -6, and the unit will be kilogram per millimeter cube because we'll be using newtons and millimeters all throughout the tutorial. And now let us go to the mechanical, define the elasticity as well as the plasticity. Go to the elastic, define the modulus of elasticity 2e5 MPa and the Poisson's ratio as 0.30. Then go to the plasticity, go to the plastic. And obviously, as already indicated, we need to feed into this the yield stress and the plastic strain correspond to the true stress strain. So let me just take these points from my Excel file. So these are the stress versus a plastic strain. It is not the strain, it is the plastic strain. Accordingly, you will find that yes, at the yield stress, you start with a plastic strain of 0. So we'll just copy this from the Excel. and we just paste it over here. Okay, Control V, yes. So I have defined my stress strain curve to the true stress strain plot. So this means that the plasticity definition is complete. Now let's go straight to the damage for ductile metals. Here as you can see that Abaqus provides different damage models. So out of this we'll select the ductile damage, and the ductile damage enter the fracture strain. Accordingly, we'll enter it as 0.24. The stress accelerator is the tension, we'll keep it as 0.33, and the strain rate will keep it as 0.001. And here you will find that there is a sub option, and this is basically used to define the damage evolution. Please remember that in the damage analysis, you have to initiate the damage, and also you should tell Abaqus how the damage evolution should happen. So press the sub option, and here press the damage evolution, and here you can see that as the Abaqus provides two methods. One is the displacement, and the other one is through the fracture energy. We'll select the type displacement, and the displacement of the failure will be specified as 2 millimeters. So this is okay for us. So this means that we have defined all the general property, elastic, plastic, damage, ductile damage, and the damage evolution. So this means that all the property definition is complete. Now having done that, let us go for creating the section as usual. We'll call it as a section steel. Section steel, okay. Continue. This is okay for me. Now create a section as usual. So let us just select all the regions over here. So done. And here this section steel is okay for me. So this means that the property definition is over. Now here I would like to do one more thing, that is as told earlier, this bar specimen need to be divided into three equal parts, and one part will be used for the clamping and the last part will be used for applying the displacement load. So this means that we have to go back to the part and let us provide the partitioning. So we'll use first the partitioning using the so-called datum planes. So let us create two datum planes. So this is the distance, enter the value. Okay, so this is flip. This is okay, and we know that the first datum plane should be at 20 mm because it is 1/3 of 60. So that is already generated datum plane. Now let us also select create the second datum plane to the value. This is okay for me, and the second value will be at 40 mm. So that's okay. So we have defined actually created rather two data plates at the required locations of the partition. Now go back to the partition here, and here select the so-called data plane. So first select the data plane. This is my data plane, okay, and create the partition at this location. Now let us create a partition in the second data plane as well. So done. Okay, let us select the data plane. So this is my data plane. Okay, so create partition. So yes, so you can see that our partitioning is done. As you can see that the part is divided into three equal parts. Okay, so now this means that we can our part is over, property over, go back to the assembly. We have to create just one instance. It's a very simple model, and we would like to create the mesh on the part itself. So this is okay for us. Now this means that we can go to the next module, that is a step module, and in the step module we need to create a new step for applying the displacement loading. So let us create a new step. So I will call it as a step displacement. Okay, and as usual this will be placed after the default initial step, and the analysis procedure that we select is a static general, though this can be solved either using the dynamic explicit or implicit. In this tutorial we will focus on the static general. Please remember that we will have a set of tutorials on static explicit and implicit later. So now let us focus just on the static general itself. Okay, you just continue. Alright, so feed all this data. Please remember there is a high nonlinear problem from the geometry aspect. So keep the NL geomass on, and to ensure that yes, there must be a good convergence. Let us apply some kind of a dissipated energy fraction through the damping, and then here the time period will be selected as 1. And coming to the incrementation, Let us use a little bit more parts, and let us keep the initial at around 0.01, and the maximum I would like to keep it as a 0.05, because this may require some kind of some convergence problems this may have. So let me keep them minimum as a e raised to minus 15. So this means we have defined almost all parameters, and in the other, if you find still the problem is not converging, you can go for the matrix storage as unsymmetric. This is also one option, to avoid the convergence issues, or to eliminate the convergence issues. So we'll keep it just like that. So the step is already defined for applying the displacement loading. Now here another important thing is the creation of the field output. Now we want to create it for the step displacement, continue. And here we need to select only the required variables, because don't select all the variables, because that makes the Abaqus to take a longer running time. So whatever is just required for the result interpretation and visualization, select it. For example, among the stresses, we select the von Mises stresses and its components, and go back to the strain. And the strain, what I would do is that I will select PEQ, that is my equivalent plastic strain. And in the displacement, I would like to have my U translations and rotations. That's okay for me. And in the force and the reactions, as I would be interested in extracting the reaction forces at the reference point, I will have my reaction force RF also here. That's okay, good enough. And contact energy going to the failure. In the failure, what I would like to have is, I would like to select one more parameter known as a scalar stiffness degradation. Okay, so select this will tell you how much portion of the static stiffness or the member stiffness is getting degraded. So this is the SDEG parameter. Please remember all this variable name SDEG parameter. Okay, that's good enough. And now what else? Go back, go here. I think that yes, here there is one more important variable, that is known as a state variable. And this state variable is important to ensure that yes, there must be what we call as a member deletion as and when the stiffness falls to the required level. So this will be initiated through a variable known as a status variable. So ensure that this variable is also made available to the Abaqus after it runs and writes to the ODB file. So this means that we have pretty selected almost all the required variables. So this is okay for us. Fine. Now I think that in the step we don't have anything else. We can go to the interaction, but please remember here, as far as the interaction is concerned, it's a very simple system. We don't have any kind of interaction or contact definitions. But in this module, what we would like to do is, we would like to define some reference point. For example, it's always a good practice. Okay. So here I will define two reference points. One is the CG of the cross section at the left end and at the right end. So let me press the reference point RP. So the first coordinate I will be defined as 0, 0, 0. That is an origin. So yes, you can see that RP1 is already generated. Go for the next one, 0, 0, 0, and we know that its coordinate should be 60. So press enter. Yes, you can see that RP2 is also generated. Now we want to tie this RP1 to this 1/3 portion. Okay, and RP2 we want to tie it, or we want to couple it to the last 1/3 portion. So this is being done through through the definition of the constraints. So go to the definition. I will define as a constraint 1, coupling, continue. Okay, and here I would like to have my okay, so interaction. Okay, I will have it as, so let me have select the constraint control point. I'll select first, this is my constraint point. Done. Okay, done. Okay, fine. Now coming to the node region, and the node region, let me just go to the cells. Now I want to tie this particular reference point to this particular length of this specimen. So done. And this I will accept it as a default settings. Okay for me. You can say that yes. Now RP1 it is a, so if you can just rotate it a little bit, you can see that yes, your RP1 is tied to this 1/3 portion of this bar. Similarly, let us proceed for tying RP2 for the to the last one-third portion of the specimen. We shall go in the same way. We shall go to the coupling, continue, and then select the control point, select it as RP2, then done, go to the node region, okay, then select this portion, select done, okay, this default setting is okay. Yes, you can see that RP2 is tied to this portion. So this means that our use of the interaction module it is over. Now let us proceed to now the module load. So now let us proceed for creating the boundary conditions. So first let us create a BC that is for a fixed end. So I will call it as BC fixed, and this will be generated in the initial time step, and corresponding displacement and rotation. This is my RP1. So I will select it, and I will restrain this end in all the directions. Okay, so that's okay for me. Finally, let us create one more boundary condition for the free end. I'll call it as a BC free, and this will also be generated in the initial step, displacement and rotations. So let us select my RP2, that is at the free end, done. And here I will allow this end to move only in this direction. Accordingly, I will keep U3 unchecked. Okay, so that's okay for me. Now let us apply a deformation of 15 mm at the free end through the RP2 through the boundary conditions. So let us create one more. I'll call it as BC displacement. Is the displacement, and this will be generated in the step displacement. Okay, fine. So displacement, rotation, continue. Now let us select RP2 as a point, done. Now here this is a U3, and the maximum value of the displacement you applied is 15 mm. And this, as already explained earlier, we want to apply it in a linear way. Okay, so let us just create a new amplitude for the displacement application. The variation of the amplitude will be described through this function. Let me call it as amplitude linear. Okay, tabular, continue, and so at a time 0 the amplitude should be 0, and at a time of 1, okay, my amplitude should be maximum, that is at 1. Okay, so this is okay for me. Now select this as amplitude linear. So we have applied a displacement of 15 mm at the RP2. So select OK. You can say that yes, the displacement of 15 mm is applied. So this means that the application of the boundary condition is over to us, and we don't have any kind of a loading acting on this rod. So let us straight away proceed to the mesh. So here, as you can see that these two are the clamp ends, and this portion is likely to subject to large deformations and stresses. So we would like to use a larger mesh density in the central portion. So let us keep first of all a uh, global shear size of 1 mm. 1 mm. Okay, apply. Okay. Now regarding the central portion, let us use a little bit more larger density of the meshes by applying a lower seed size. So this, which can be done through the local seed size. So we can select the edges where we want to have a smaller size. So these are the edges. So I'll just select it. Okay, fine. And this we would like to keep it rather than 1 mm. We would like to keep it a smaller one. That is a 0.5 mm. So keep it as by size. Keep it as a 0.5 mm. 0.5 mm. So apply. Okay, fine. Okay, fine. Now let us proceed for applying the mesh controls. So let's select the entire rod, and as is a very simple model, we want to apply the structured mesh only. Okay. Now coming to the selection of the element. So let us select the entire rod. Done. And here remember we are choosing a standard element library, 3D stress. Geometrical order for this problem can be kept as linear, and here we don't want to go for the reduced integration, okay, because this is a highly nonlinear. I don't want to go for the reduced integration method. So now here there are two important parameters which you need to include because this is a damage analysis. So there is an element deletion option. Rather than user default, keep it as yes. Means that as and when the stiffness is okay decreased to the level specified level, we won't delete those corresponding elements from the model. So keep this as yeah, means that element deletion as yes. And coming to the maximum degradation, let's just specify it very clearly. I want to keep the degree of damage to 0.3. That means 30% of the as and when the damage reaches to a level of 30%, the corresponding elements will be automatically deleted from the model. This gives us a very good, uh, visual impression of how the stiffness deterioration takes place all throughout the model. So this is okay for us. Okay, so now let's proceed for the machine and the part. So yes, okay, fine. You can see that yes, the central model, the central portion of the model is having a message of 0.5 mm, whereas the rest of the model is provided with a global seed of 1 mm, and we have provided the proper mesh control as well as we have assigned the proper elements. We have also enabled the mesh deletion, that's element deletion, and also the damage level association as 0.3. So we can straight away proceed for creating now the job and then later submitting it and running. So let us create the job. So I'll call it as create, call it as job R1, job R1. Okay, fine, continue. So all these parameters are acceptable to me. Now I can proceed for the submission. Okay, so you can submit it. So you can see that the status is submitted. And now once the processing of the input file is over, it will start proceeding for the calculating the model. So accordingly, you will find that yes, it is the status is currently running. Okay, fine. So let us proceed for reviewing the results obtained from the damage analysis. So first, let us proceed to see the Walmart stresses. Okay, so let me just zoom a little bit so that we will be able to see the damage that is happening in the central portion. So you can see that look into the central portion. You can see that as the time changes, you can see that yes, the Walmart stresses goes on increasing. Yes, you can see that the elongation has started taking place in this central zone, and the elongation goes on increasing. You can see that currently the Walmart stress is on the order of 700 Newton per meter square. Okay, you can see that yes, the elongation goes on increasing, and at this point you can say that yes, the breakage of the specimen has taken place. So let me just zoom this once again for you. Yes, so how the damage progresses in the central portion, you can see that yes, the elongation goes on happening, yes. So finally, the rupture takes place. You can see that yes, this is normally this is a kind of the surface that we also observe during our experiments. So this is all how the damage propagates in the. This is very simple model that is subject to pure axial tension. Now, having done this, so let us proceed for examining the other variables, of which I would like to show first of all the equivalent plastic strain. So as we know that the equivalent plastic strain is a measure of how much plasticization has taken place in the damage model. So let's proceed on seeing this. We can see that yes, the plastic strain goes on increasing the central portion. So you can see the currently it is at 0.016. It goes on increasing, yes. So at this stage, you can see that even it has reached up to a level of 1.03. So yes, it goes on increasing. Yes, finally the rupture has taken place. You can see that almost say 1.715. So the current plastic strain is has undergone is a very large number we are getting, right? So this is all regarding the equivalent plastic strain PEEQ. The one variable which I would like to show you is the static degradation variable. So if you remember, we have set the static degradation to a maximum level of 0.3. So now let us see how this static degradation or the degradation, it propagates throughout the central portion. So yes, you can say that yes. Now the static degradation is 0.157, and you will see that when this variable reaches approximately 0.3, the full rupture takes place. Yes, you can see that yes. Now it is around 0.316. So that's a 0.3. Yes, you can see that around 0.309 total rupture has taken place. And if you remember, we have also set one variable which is known as status, and that should be 1.00 or throughout. This is how you should check the status variable while reviewing the results. Now, having done the review of these important variables, let us proceed for obtaining the load displacement curve for this specimen. Or in other words, we would like to know what is the tensile carrying capacity of this small specimen, and how this the capacity changes all throughout the duration of the analysis. So let us, for this purpose, let us first of all extract some useful data at this reference point RP2. So create Excel data. So go to the ODB field output, continue. Now, obviously, what we need to select the position as a unique nodal. The variables that we are interested in is obviously is the reaction force in the z direction, that is RF3, and we are also interested in the displacement, the spatial displacement in the z direction, that is a U3. So let us select these variables, that is the RF and U in the z direction. Now let us select the element or the nodal point. So the nodal point I want to select from the load labels itself. Let me just highlight this also. I want to select this data for my reference point RP2. So you can say that save. You can say save. You can say that this, yes, this is the point. Okay, fine. So we have extracted the reaction force U data, that's the displacement data for this reference point RP2. Now let us just do some kind of an operation. Let us combine these two data in order to form a simple XY graph. So again, go to the XY data, plus the operate XY data. Okay, so continue. And here, let us use the operator known as the combine, so that we can combine the two data that is already extracted in the previous step. So use the combine way operator, and first on the x-axis I want to have my displacement. So I will select my first displacement variable u3. Okay, I'll put a comma and then select the second displacement variable. Okay, now you can just plot this expression. How does it look like? So look here. So you can see that this is the load deformation capacity of this, the load displacement curve for this specimen in tension. You can see from this graph that yes, the capacity of the specimen at the ultimate state is of the order of say 15 kilonewton, and this ultimate capacity is mobilized at a displacement of around say 3 to 3.5 mm, and you can see that the degradation of this capacity has taken place at around a displacement of 8 mm, after which you know that the rupture has taken place and the resistance has dropped down to 0. So this is how you should analyze the capacity of any component, and this kind of damage analysis is very useful, especially in the structural stage as well as the reinforced or the composite concrete steel connections, wherein we'll be able to visualize the damage with the local components, and we can very well tell the capacity of this particular joint configuration is governed by a particular component. Okay, and the decisive rotation or the capacity level of that particular component or the connection. So there are many other what I want to say, that analysis to be carried out in the damage propagation analysis. And remember that Abaqus uses the so-called CDM, that's a continuum damage mechanics model for the damage analysis. There is also another branch known as the fracture mechanics that is altogether different. Probably I think that in the next tutorial I would like to put up a small simulation which shows simultaneously the propagation of the damage in the model along with the relevant XY plot. This could be a small video which hardly runs for 30 to 45 seconds. So obviously in the coming weeks you can expect a very interesting tutorials. Till then, bye.